All right, let's talk about recursion. It's one of those concepts in programming that sounds, well, kind of scary, right? But I promise, once it clicks, it's like unlocking a new superpower for solving problems. So let's just dive right in and demystify this thing. So, how would you even explain an infinite reflection to a computer? You know that effect, right? When you stand between two mirrors and you see this endless tunnel of reflections getting smaller and smaller into infinity? How on earth would you tell a computer to draw that? Well, that's exactly the kind of problem where recursion shines. It's all about tackling a huge, seemingly infinite problem by noticing that, hey, it's just the same smaller thing happening over and over again.
So here's our game plan. We'll start with what recursion even is. Then we'll cover the two golden rules you absolutely have to know. After that, we'll get our hands dirty with a couple of classic examples, Factorial and Fibonacci. And we'll wrap it all up by talking about how to actually start thinking recursively. All right, section 1. So what is recursion really? Let's just forget about code for a second and use a really simple, non-technical analogy to get the main idea across. Okay, so picture this. You're at the front of a massive conga line, and you want to know how many people are in the whole line. Now, you could walk all the way to the back and count every single person, but that's a lot of work. So instead, you just turn to the person right behind you and ask, hey, how many people are behind you? And what do? They do the exact same thing. They turn to the person behind them and ask that same question. And this just keeps happening all the way down the line. In that conga line, that's recursion in a nutshell. It's a process where you solve a problem by using a simpler version of the exact same problem. In programming, it's a function that calls itself, breaking a problem into smaller, identical pieces until it hits a piece that's so simple it can be solved instantly. Just like the last person in the conga line, who knows, hey, there's 0 people behind me. They don't need to ask anyone else. Okay, so this is where it gets really important. For this whole thing to work and not just go on forever, like those infinite mirrors we talked about, every single recursive solution has to follow 2 golden rules. Seriously, if you get these 2 things down, you've got recursion. So here they are, the 2 essential parts. First, you have the base case. Think of this as your emergency brake, your stop sign. It's the simplest possible version of the problem that doesn't need to call itself to be solved. In our conga line, that was the last person. Without a base case, your function will just call itself forever and everything crashes. Then you have the recursive step. This is the action that repeats. It breaks the problem down a little bit and then calls itself with that smaller piece. Critically, this step must always move you closer to the base case. All right, theory is great, but let's see this stuff in action. We're going to put these 2 golden rules to the test with a classic programming problem, calculating a factorial. So what's a factorial? It sounds fancy, but it's really simple. The factorial of 4, written as 4 with an exclamation mark, is just 4 times 3 times 2 times 1. But here's the recursive part. You could also say that 4 factorial is just 4 times whatever 3 factorial is. And what's 3 factorial? Well, it's just 3 times 2 factorial. See the pattern? The problem is defined in terms of a smaller version of itself. It's a perfect candidate for recursion. So let's visualize how the computer actually handles this using what's called a call stack. We first ask for a factorial of 4. It can't answer yet, so it says, okay, I need 4 times whatever factorial of 3 is. It puts that on hold and calls factorial of 3. And that call says, hold on, I need 3 times factorial of 2. You can see the stack building up, right? This goes all the way down until we hit factorial of 1. And that's our base case. It knows the answer is just 1. It doesn't have to call anything else, so it returns 1. Then the whole thing starts to unwind. Factorial of 2 gets its answer and returns 2. Factorial of 3 gets its answer and returns 6. And finally, our original call, factorial of 4, gets the value it was waiting for. And boom, there it is, 24. The whole stack of questions resolves itself, and we have our final answer. Now, you might be thinking, couldn't I just do this with a simple loop? And you're absolutely right. You totally could. For a problem like this, a loop might even be a little faster. But the point here is the way of thinking. The recursive approach is often seen as more elegant because it directly mirrors the mathematical definition. It's a top-down approach of breaking things down versus a loop's bottom-up approach of building the solution. All right, ready for level 2? Let's tackle another super famous example, one that's basically the poster child for recursion, the Fibonacci sequence. You probably know this one. In the Fibonacci sequence, each number is just the sum of the 2 numbers that came before it. Simple, right? But think about what that means.
If we want to find the fifth number, we need to know the fourth and the third. And to find the fourth number, well, we need the third and the second. The recursive pattern is literally built right into the definition of the problem.
Now, this time it's not a simple, straight line like the factorial stack, it's more like a tree. To get fib5, our function has to make two calls to itself, one for fib4 and one for fib3. And each of those calls branches out again. It's this expanding tree of calls. This whole thing keeps branching out until every single path finally hits one of our base cases, which are fib1 is 1 and fib0 is 0. Once all those leaves of the tree have their simple answers, the results start getting passed back up, getting summed together at each node. And after all that branching out and summing back up, the entire tree collapses down to one single number. And for the fifth number in the sequence, that number is 5. So, okay, we've seen how recursion works in a couple of examples. But the bigger question is, why does any of this matter? I mean, is it just a clever party trick for programmers? No, not at all. It's really about learning a completely new way to think about and solve problems.
So here's what I really want you to take away from all this. Recursion is your best friend when you're facing a problem that's naturally self-similar. Think about navigating folders on your computer. Every folder can contain more folders, which is like a mini file system inside a file system. That's a recursive structure. So when you find a problem like that, remember the two golden rules. Number 1, figure out your base case first. That's your exit strategy. You have to have an exit. And number 2, make sure your recursive step is always making the problem just a little bit smaller, getting you one step closer to that exit.
Learning to think recursively is a skill. It's like building a muscle. It's about training your brain to look at a big, messy problem and ask, is there a smaller, identical piece of this same problem hidden inside? And once you start looking for it, I guarantee you'll see this pattern everywhere, in data structures, in nature, in art. So my question to you is, now that you know what to look for, what problems are you going to solve with this new way of thinking?